Okay, in absence of any real coding work that I've done in recent years, today I just have to present some stuff I was interested in, and so I'm going to talk. I wanted to talk a little about non-dimensionalization, because I found myself very often in a situation where when you add a feature, or when I ran some cases that I tried to run with non-dimensionalization, and I ran into problems so frequently that I got to the habit to always run dimensional. And so I wanted to take some time to understand a little bit more the code behind it and the logic, especially for compressible flow, because I use that much less than compressible. I need to click it.
That's not there.
Somebody who's still, you can. Okay, and of course, first off, the non-dimensionalization I'm talking about is that any input we get, especially from the config, but also from other files, which I represented here as a generic phi, we divide that value by a reference value to get the non-dimensionalized value. And then we go into our solver, and in this solver, we only use the non-dimensional value. And once you are finished with solving and you want to display, or you want to look at, again, dimensional values, you simply multiply the non-dimensional value by the reference, and then you get the dimensional value back. And unfortunately, at the current state, the redimensionalization, so the last part here, that is not done by SU2 automatically. So when you look at a volume solution and you non-dimensionalize with the pressure equal to 1 in the compressible case, you will see in your volume solution that the pressure at the far field equals to 1. So that already is maybe a little caveat there. And the way I think most of you interact with it or have seen it, even if you run dimensional only, you will see this little table in the screen output, and it gives you always the dimensional free stream value, then the reference, and the final non-dimensional value that the solver works with and that the solver will eventually also output. And this is also a great tool if you're unsure what the non-dimensionalization is doing or how you redimensionalize in your output. You can just look at this table, or also grab the values from the screen and write a script so that it transforms it automatically, in case you don't want to do that with the paraview calculator all the time. And now also the question is, how is this non-dimensionalization really going on? This division by reference value, how is the reference value determined? This is just the way we do it, and it's, as you might have seen in some other paper, we base our non-dimensionalization on a non-published paper from a person that once was in Stanford, I think. So I think that document is not publicly available. I think that's also something we might want to publish somewhere. And how we do it, we have a set of primary both reference values, and these are user input. They are not specifically always direct user input, but sometimes indirectly via some other options that you can pick. The other ones that are here in the second part of the table, they are computed based on the reference values that are given here in the primary, and yeah, just computed from those. You see already that I added some notes. For example, the reference length is always 1, and it's not set by ref_length. So there's, I would say there is quite a bit potential for confusion in the current setup. The ref length and other reference or ref_values we use are purely for coefficient and momentum computation. So don't think, if you see a reference or ref length in the code somewhere, that it's necessarily this option, although it's basically the exact word. And you see, for example, velocity, we use only, or the reference velocity as a primary input is only used for incompressible. And therefore, you see here velocity is in the primaries and in the secondaries, because if you switch between the solvers, it becomes a primary or a secondary. Yeah, and the problem is also, for example, in this force ref, it changes between the compressible and the incompressible case. And I would always say, in doubt, if you don't know, or if you're unsure if that table, which is also on our website, is correct, I would always recommend that you go into the set non-dimensionalization routines in the specific solver and look for yourself. And now a little bit to the immediate effect you will see when you use non-dimensionalization. And I this how to get convert, or how to convert in 7th order of magnitude more. Because what's happening, we scale every input with this reference value. We bring especially energy and density very close together in terms of value, where it is usually 5 or more orders of magnitude apart in absolute value. And this has a great effect on the convergence plot, on the residuals, although there's no noticeable difference whatsoever in the output that you look at, or in the non-dimensional coefficients like lift and drag. So the solid lines here, it's just the income, or the invested NACA 0012 quick start that we all come to love. And yeah, the solid lines, they are dimensional, and the green line here is the total specific energy residual, and the blue line, that is density. And here we kind of see the effect of a value, and that absolute is 10 to the power of 5 and 1. So that will naturally differ. And now if we non-dimensionalize, we bring all those values, the energy and also the density, although the density we wouldn't necessarily have to non-dimensionalize it. It brings it all very close together in value, and thus the precision we have in that value range is matching. So we get, because it's all coupled, very similar convergence. And if you just would, for example, a residual stopping condition on energy, you would see here 7 or 10 to the power of, or you'd see a convergence in the log 10 residual of minus 7.5 compared to nearly 15. So suddenly, you change non-dimensionalization, and your simulation doesn't converge anymore, or converges super quickly. So you have to be aware of that when you change non-dimensionalization. You greatly tamper with your convergence conditions. That's also a reason why I always prefer to have at least one residual condition and at least one relative objective function condition to assess convergence. Either of one can give you a false sense of whether your simulation is converged. If you look at the residuals and the results, that's all fine. But if you run an exploration with a couple of 100 simulations, you don't look at all the results, and you just trust your scatter plot that you get, and you might have some simulations which are completely bogus. So that's why I always like to set both stopping conditions. And just for the sake of completeness, because it's a compressible case, we have certain types of non-dimensionalization. So we can set the pressure in the far field to 1, we can set the velocity to 1, or the velocity equal to the Mach number. And in the cases I ran, in particular, I found that within these non-dimensionalized simulations, I saw very little change in terms how they perform, but the big change always to the dimensional simulation. So, but I'm pretty sure that I haven't covered all extreme cases, and I don't know, for example, hypersonic, maybe these characteristics are important also to consider within the non-dimensionalization schemes. And now a little bit to the specific setup, because especially for compressible flow, the non-dimensionalization and the initialization is somehow linked. And when I looked at the code, I pretty quickly got lost and scratched my head of what's actually going on. And just as basically as a best practice guide in that regard, I would always go and set because what we do, we always in compressible go through free stream options, and we have options that change how the free stream options are chosen, free stream quantities are chosen, and then based on these free stream values, we do the non-dimensionalization and the initialization. So with these free stream values, you change both non-dimensionalization and initialization. And so the best flow chart I can come up with is you choose the free stream option. So you basically say whether temperature or density is computed from your thermodynamic state. Then you have an initial option that you have the possibility to either reuse your thermodynamic state for that, or you specify a Reynolds number and a Reynolds length that set the thermodynamic state. And then the last one I would choose is the dimensionalization, because that will just then say how these free stream quantities that you set through these two options and the remaining free stream underscore, for example, pressure option, that will determine how these are scaled, so that at the end of the day you will have the pressure at the free stream that is 1 or velocity that is 1, and the rest then acts accordingly. And also another linkage here is the far field marker is also bound to then these free stream values. So when you have a compressible simulation with a far field, you're pretty much safe in that sense that it's tougher to mess that up. But if you run internal flow scenarios, you might need to have more caution, because these free stream values can get out of touch with the simulation you're actually doing. In incompressible flow, the setup is a lot easier. So we have a set of inc, and there's like velocity, temperature, and density. And you set these values, and these are always initial values. That's a big difference to compressible flow, where the initialization is directly bound to the free stream options. So you hard set the initial options, and then for the non-dimensionalization, you have the possibility to reuse these initial values or use reference values. And actually there on the slides, I also got confused. And then because it's actually inc underscore velocity underscore ref and not ref underscore something. So I also maneuvered myself there in a pretty bad situation. But all in all, the incompressible, or for the heat equation, because we reuse the heat equation solver also to solve a weakly coupled heat equation to the incompressible flow, but also for the standalone solid heat conduction, it reuses these incompressible values. If you say I exclusively use the FEM elasticity solver, then you're in luck, because then nothing of that applies to you, because we don't have any non-dimensionalization, and the initialization is always displacement 0, but I suspect there's not many FEM elasticity only users here. Some best practices I would consider when you work with non-dimensionalization, one from the simulation aspect and then from the coding aspect. So yeah, of course, naturally choose your reference value in the order of magnitude of value that you expect in your flow domain. That should be rather straightforward, I think. And from what I've seen, it's not especially necessary to hit a perfect value. So if you have a temperature delta of 300 or temperature delta of 50 Kelvin, you can, or you shouldn't contemplate which value in that temperature range you choose, as long as you hit the order of magnitude. I think from the core benefits of added precision, you are already safe. And of course, as much as I would always like to trust the SU2 solver, I think it's a good idea if you have a new case that you confirm that the non-dimensionalization actually works, or at least that you see identical or similar results between a dimensional and non-dimensional simulation. So you just run the dimensional, the non-dimensional, and you have to manually redimensionalize, as I said. You can do that with the screen output, and then you can compare these results. And if you have 8-digit differences, that's probably fine. But if you see larger deviations, either or chances are high that something in the non-dimensionalization is going wrong, because we also have non-dimensionalization going on in turbulence models, in transition models, so that can become very complex very quickly, and there might be some hidden errors in your specific set. And from coding, of course, everything in the code that you pull from config. So if you config dot or dash get, I don't know, marker wall temperature, then you should have an urge that you need to non-dimensionalize that. So whenever you do that, non-dimensional. If you don't, if you have a value, we have quite a good set, I would say, that covers most viscosities, heat fluxes, forces. So then you can always pull from the config also a reference value. If you have a new quantity and a new value to non-dimensionalize, I actually don't know what the best approach is. So I would say that you get creative and test your case with this pattern or with this pattern. And if you find that you cannot do that, you should just not allow it. And all values from files are dimensional allowed as well. Okay, I should leave too soon. Yeah, and everything that you get inside the solver, that's already dimensional, and you don't have to worry about that. Only, yeah, keep that in mind for debugging, because I was there and wondered why my temperatures are 1. What is going on, until I noticed, okay, I have non-dimensionalization on. And also fluid models, I think I saw some fluid models that are excluded from non-dimensionalization. And I always like that if I see that people care about, okay, I tested that and I excluded it so that every new user will not run into any of these issues. So to wrap it a little bit up, the takeaway, of course, just run dimensional and forget about it. Of course, that's not true. But be aware of all the options you have to set, and also which options you not have to set for a working non-dimensionalization setup and initialization, and also check for defaults. I saw a lot of config files in the repo that relies on the defaults, and I'm always not sure whether that's intended use. Yeah, and make sure you get reasonable results and just match it. And now I'm actually interested if people here have cases where they say, okay, I need non-dimensionalization. If not, it completely fails or it's really bad. So I'm interested in those cases. And I'm interested in cleaning a little bit the code. Although I noticed more and more it's pretty, it's a pretty complicated setup, and to untangle everything is probably hard. But we have a lot of code duplication going on, so I want to work on that. And that wraps my talk. And yeah, I'm looking forward to getting to work on that and to see what the community has to say towards non-dimensionalization and the usage. Thank you.
We have time for one question. No, I have to ask you a quick question. So I didn't fully get what are the next steps.
So
investigation.
Yeah. So my thought was we currently have a completely separate incompressible non-dimensionalization setup from the compressible one, and I have the feeling that we can, especially for initialization, we can merge some options so that we do not have to completely switch everything when we switch flow regime. And the other thing is, just if we do not set, or if we do not change anything from the config perspective, I think, or especially in the NEMO solver, that completely re-implements the non-dimensionalization routine and adds, I think, vibration temperature. So I think and also the higher order method solver does the same. So I think we can probably, pull the code up into a high level and reuse the code for multiple solvers. If at least we do one thing, we should do that. And another thing is maybe, if that is wanted, to add the redimensionalization to the code itself, so that as a user, you never see non-dimensional values except for the screen code. You always at the end get the dimensional values. But that would be